and welcome to all of you for today's lecture. As we are doing the examples from Pericyclic and Spectroscopy, today's first example is C9H12 molecular formula and 3 signals in proton noise decoupled CMR. The probable structures are given over there: 1 2 3, 1 2 4, 1 3 5, and then this is ethyl methyl benzene. So 3 signals is there should be 3 sets of carbon. So A, B and C, these are the 3 sets of carbon. So in proton noise decoupled spectrum you will get 3 signals, one for methyl, second is for methine, that is CH, and third is for quaternary carbon. So 3 signals. So the correct structure is 135 trimethyl benzene or mesitylene. Okay. Then second one is C5H8O4. Only 2 singlets in PMR. Now singlets means there should not be a coupling between the neighboring protons. So if you look at this will be A and this will be B, but if you look at the sites of unsaturation, here sites of unsaturation are 2, here it is 3 sites. So this is wrong, although it looks okay, but C5H12 minus C5H8, 2 sites of unsaturation, 2 are because of these 2 carboxylic acid group and third is because of the ring. So that's why it is wrong. Same is here. Here also we have one set. I will put A, this is B, this is C, and this is D. So that's why this is also wrong. This is only 2 sets, A and B, both singlets, because methyl protons are devoid of neighboring partner, and COH protons, as we know, they won't couple. So this is the correct structure. This is correct. Here this is correct. Moving on to the third example, C8H16, the molecular formula, one site of unsaturation in that, and then quartet, triplet and doublet is given. Now this doublet means olefinic doublet or aromatic doublet. With C8H16 both are possible, olefinic as well as aromatic. Only 4 signals are seen, 4 signals. So this should be double. So that's why we can account for 8 carbons. So that means we are working with a symmetrical molecule. So symmetrical molecule, if you look at the 4 options, let us start from the last. This is not symmetrical because it has olefinic protons, but we don't have, we have so many methyls and methylenes. Same is here, same is here. There are 4 sets, A, B, C and D. So 4 sets equivalent, 130 can be assigned to the CH, then 39, 23 and 13.7. As you go away from the double bond, the chemical shift value of the carbon decreases. So this will be 39, this will be 23 and this will be 13.7, the methyl will be quartet, these 2 will be triplet and this will be doublet in olefinic region. Okay. So correct option is once again the first one. Okay. Then fourth example is C8H10O. These are CMR values given: quartet, doublet, So if you look at the higher values like these 125, 127, 129, 146, they are all aromatic carbons, because these are CMR values. They are aromatic carbons, these are aliphatic doublet. So quartet means CH3, doublet means CH, probably attached to oxygen. That's why it is deshielded. And if you look at the and one more thing you can derive from this is 2 to 4, 5. So it is mono-substituted ring, because you can see 5 CH and this is quaternary carbon in the aromatic region. So mono-substituted means we can think of this kind of pattern. So we have A, B and C. 3 types of carbons are there. So 127, 129. So if we are having donor here, this will be 127, this will be 129 and para will be 125. So that is how the distribution is. 146 is this one, where you are having a quaternary carbon. Doublet is there. Now this is doublet, and you have got methyl also, because methyl will be quartet, and we are left with OH. Because OH is there and phenyl ring is there, this methine proton or CH proton is deshielded, that is 70. 23 is, this is just like you are having CH3 attached to carbonyl group, so that is fine. 23, 70 is this, and then 127 because you are having donor, 129 and 125 is the para. That is how the distribution is. So the correct structure is first. Okay. Now moving on to the fifth example, C5H10O, 30.2, 31.9, 61, and then so negative means and positive only one is there. So if you check these values, 61.8 is methylene. Actually this depth 1, depth 2 should be there, but only this data is given. So on the basis of this, these two you can say that these are olefinic carbons. This is maybe OCH2 more probably, and then these are, this may be CH3 and this is CH2. So if you look at the values A, B, C, D and E, all 5 you can explain with first structure. It's okay, but OCH3 is ruled out because OCH3 will be 55 something, that is missing. So OCH2 is fine, that is 61.8. So the correct structure is first one. Okay. Now the next one is based on pericyclic. This diene is, or you can say trine, because this is exocyclic bond, is treated with, so thermal will be 4+2, and they are asking about major product of Diels-Alder. In this case, the internal double bonds, they will act as a diene. This is out of conjugation, and in all probabilities we will be having this compound as a major product, that is endo product. This double bond remains out of the competition, and in under thermal condition 4+2 is more probable, the same compound you can draw like this. This is away, so that is away, and now you can have your dinophile here, so you can easily show the formation. Okay. Then next one is this diene, or this is your isoprene, this aldehyde, acrolein, and heated, and the major product is expected. The major product has to be this one, and the others are like these two are not maybe minor product, but they are not major product. So this is the, so this is all for today. Once again, next lecture I will start with some other topics, because we have to do 13 chapters, so we will do slowly, and if require some basics also I will cover wherever it is necessary. Okay. Thank you very much.